In this video, we'll begin looking at how to use Biot-Savart law to find the magnetic field of a current-carrying wire. And so to begin with, let's consider first the magnetic field of a charge q moving with speed v through space. Specifically, we'll look at finding the magnetic field at a point P, which is a distance r away from our current position of charge q. And so we can define the distance r. We can define the vector r, and therefore the vector r hat, or the unit vector r hat, which points towards P. And now at this point, our magnetic field will be mu naught over 4 pi, which is a constant. It will be proportional to our charge q. It will be inversely proportional to the square of the distance. But then, as we can see, it is proportional to v. As the magnitude of v increases, our field increases, but we've got a cross product here, v cross r hat. And so let's first recall that the magnitude of the cross product, a cross b, is equal to magnitude of a, magnitude of b, sine theta. In this particular case, our second vector r hat is a unit vector, so v cross r hat just becomes magnitude of v times 1 times sine theta, where theta is actually the angle there between v and r hat. So it simply becomes v sine theta. And so in magnitude, we can say that magnitude of b is equal to mu naught q v over 4 pi r squared sine theta. And just to consider some limiting cases, what this means is, considering a fixed distance r, if we go another fixed distance, sweep out a circle right here, if we are right here at an angle of pi over 2, our field will be maximal. If we're directly in front of the particle, our field will be 0, since sine theta will be 0. We also want to consider at this point the direction of the magnetic field. And there are many options for doing this. I highly encourage you to look up, if you would like to, right-hand rule. But since I can't demonstrate with my hand in this video, what I usually do when taking cross products is use the IJK approach. So we're going to define 3 unit vectors. I hat is going to denote our positive x-axis, j hat is going to denote our positive y-axis, and k hat will be coming out of the page. If I want to take a cross product, then I can say I cross j, j cross k cross I, all follow our arrows. I cross j gives us k cross k gives us I, k cross I gives us j. Furthermore, the cross product is anti-commutative. So if I want to compute j cross I note that we are going opposite the arrows. I cross j would give us k. Therefore, j cross I gives us negative k, and so on. So k cross j would then give us negative I. And so let's look at how that helps us understand the direction of the magnetic field in this particular scenario. What we have over here is a v, which can be broken down. I won't be doing this formality every time, but our vector v is equal to magnitude v cos theta I hat plus v sine theta j hat. Then our vector r hat, it has got magnitude 1, and it points entirely in the I hat direction. So r hat is simply 1 I hat. Those are our 2 vectors. I'll now go ahead and take the cross product. V cross r hat is equal to v cos theta I hat plus v sine theta j hat cross I hat, and the cross product follows the distributive property, so we can simply just distribute. So v cos theta I hat cross I hat, well, I hat, a vector cross itself gives us 0, right, because they are parallel. So we get no contribution from this term. And then v sine theta j hat cross I hat, well, I'll write it as v sine theta j hat cross I hat. And looking at our chart, j cross I is anti our arrow. Therefore, we get negative v sine theta k hat. And so all that is telling us is that our field points into the page. Now, do we need to do all of this math to actually get the direction of the magnetic field? No. although sometimes it is useful if you're dealing with a rather challenging problem to sort of break it down at this level. But in this case, note that we got the magnitude of we got the v sine theta term, which showed up in our cross product, right? Just by considering magnitude. And so a quick and dirty way to just get the direction is to say, okay, I know v has components in the I and j. I know r has components in the I. Therefore, the surviving cross product term will be j cross I. We don't need to go through the full breakdown. All right. So our result is that in this particular case, our magnetic field is B equals mu naught QV sine theta over 4 pi r squared times negative k hat. Now, this was all the lead up. What we now want to do is transition to looking at the magnetic field of a current carrying wire. And so let's consider the simplest possible case. This might not look simple, but we'll discover that it is in fact quite nice. So let's consider a wire, which is a circle carrying current I, and it's got radius r. And we're going to try to find the magnetic field at the center of the circle. So first, let's write down Biot-Savart law in full. We're told that dB is equal to mu naught over 4 pi r squared I dl cross r hat. And so what does this actually mean? What this is telling us is consider your wire. Take a small section of the wire, dl. Consider for that dl, it's r hat, the vector which points from dl to the point at which we want our magnetic field. And then its contribution to the magnetic field will follow this equation. To get the entire magnetic field, we'll go ahead and integrate. That's our goal. At first glance, this might seem intimidating, so let's break down the steps. As our first step, always we draw a picture, which we've already done. So as our second step, we'll want to focus on what dl cross r hat is. So to begin with, it's always useful to first look at what the magnitude of dl cross r hat is. In this case, magnitude dl cross r hat is magnitude of vector dl, which is just our arc length dl, times magnitude of r hat, which should just be 1. And lastly, let's pay attention to what our angle here is. We'll note that over here it is a 90-degree angle, and that will not change as we go along the circle, because note, dl is tangent to the circle, and r hat points along the radius of the circle, so they'll always be perpendicular. And so in this particular case, dl across r hat simplifies greatly. It is simply dl. Lastly, we want to consider the direction of this and see whether that changes as we go along the circle. And so let's consider a nice point. Maybe I'll consider the point right here. Here we have dl, here we have r hat. And so we can see that dl points in the negative j direction, r hat points in the negative I direction. Looking at our cross product rule, ijk, we are going anti our arrows since we're doing j cross I, and then we have an additional double negative. So overall, we end up with a negative k. Our field is going into the page. And I leave it to you to confirm that this will not change as we consider different contributions along the wire. So we've completed step 2. dl cross r hat is equal to dl times negative k. And so that leads us to step 3. We don't need to worry about vector addition because in this particular case, our components all point in the same direction. In a future video, we'll look at a case where we do need to consider vector addition. And so in this case, I can say that B in magnitude is equal to mu naught I over 4 pi integral dl over r squared, having pulled out all constants. Before we proceed from here and consider rewriting dl in terms of a more specific coordinate system, it is always useful to ask the question, does anything vary with the variable of integration? And in this particular problem, nothing varies with variable of integration. So that's always step 3. Check whether you actually need to do more. And so here, what we notice is that r is simply the radius of our circle. And so we can pull it out of our integral. We simply get mu naught I over 4 pi capital R squared integral dl. And of course, integral dl is simply the full arc length of our circle, or 2 pi r. And so we're left with mu naught I over 2r. And in direction, we're into the page, negative k hat. So in the next couple of videos, we'll look at additional examples of Biot-Savart law. We'll look at cases where not all of our components go in the same direction, right? Which we've already seen with integrating electric fields that we potentially need to evaluate two integrals, but we'll leave it here for now.